So now our first speaker can share his monitor, can prepare. Alexander, could you stop please sharing?
Yes.
Yeah, so monitor is shared. So maybe you should start record now.
It's recording already.
It's already recording, yeah? Okay, so, and ladies and gentlemen, it's my pleasure to present first speaker. This will be Professor Markus Huber from the Technische Universität Wien from Austria, and he will talk about thermodynamics limits of measurement. So, Professor Huber, please.
Okay, well, first of all, I also want to thank the organizers for putting together such a nice event in the face of such incredible adversity. And I mean, being the first speaker, I feel like I can't really start my talk without addressing some of the terrible events that have unfolded in the past month and are unfolding now. I mean, well, I'm honestly at a loss of words. I mean, I think whatever I say, it cannot be adequate or convey what any of us truly feel. But, well, notice, I also, words fail me for the profound content I feel for this maniac, for the autocrat, unleashing decades of lies and propaganda leading up to culminating in this unjustified attack and murder and destruction. I feel with you. My heart goes out to everybody that is affected. And if there is anything we can do academically to help with exchange programs or anything, please reach out. I mean, I think there is a lot of enthusiasm for more collaboration on that thing. But then, again, I'm happy, and since I have little time, that in the strength of spirit, there is this workshop put together with such a nice program, and I'm very happy to see that. Okay, so much for addressing the elephant in the room. Let's move on to science. So I wanted to give a very low-key, hopefully broadly understandable introduction to a particular subfield of quantum information and quantum technologies that might not be as broad, but it's nonetheless full of very exciting basic science questions. And it's also concerned with some of the underpinnings of quantum technology. And what I want to talk about is quantum thermodynamics. So if you allow me, I'm gonna do a whiteboard talk. So quantum thermodynamics, it sounds almost oxymoronic when you first hear it, right? Because usually, I mean, thermodynamics are these emergent, effective laws that emerge once you go to the classical scale. And yet we know that the fundamental physics, the world is quantum. So we need to understand how these laws emerge effectively and essentially what they tell us about the prospects of quantum technologies. And why is that relevant? Well, in the end, one of the major obstacles to, for instance, quantum computing and quantum simulation is the stabilization of quantum information, the preparation of pure states, the cooling of quantum systems, and really understanding the intricate microscopic dynamics behind refrigeration, cooling, erasure of information, measurement, and so on and so forth, is in some sense also key to really developing quantum technologies, but also in pondering about the fundamental limits. So what exactly do I mean? I thought I'd give an introduction because I think even most bachelor students will have heard of the famous three laws of thermodynamics. I will present them in a very simplified style and tell you why they become very interesting or debatable things in the quantum realm. So let me just start with the first law, often kind of misquoted as the energy is always conserved. I mean, yes, that's kind of part of it, but it's a trivial consequence of time evolution being generated by the Hamiltonian, which also gives you the energy of the system. A more interesting way to think about the first law of thermodynamics is that any change in energy can essentially be attributed to a change in what we call work plus a change in heat. So, okay, no matter the sign convention, sometimes there's a minus or a plus, depending on whether you take work or heat to be taken from the system or introduced into the system, but that doesn't matter now. But at the heart of it, it basically tells us that energy comes in two forms. One that is kind of usable, exploitable, that we call work, and the other one that essentially is lost to us, that is heat. Now, what this really tells us is that the way we can use energy highly depends on what we know about the state of the system. And in a classical sense, this becomes entirely objective, because what we can know about the system is given by really few observables. And essentially, no matter the microstate of the system, almost everything is always well described by so-called equilibrium distribution, by a so-called Gibbs distribution. So we can, in some sense, assume most of the time that most things are essentially thermal. That is, we can assign a temperature, right? This is something that is not true for individual quantum systems and not true for out of equilibrium quantum systems or any out of equilibrium system. But, and in the quantum realm, this makes for a very interesting problem. To be more precise, like later progress in stochastic classical thermodynamics showed that in microscopic systems, the work performed is no longer always a deterministic function. So, I mean, if I think about very classically, right, like performing some work, I might have a pulley and some weight on it. And if I manage to lift the weight, then, well, I've done some work. And if I drop the weight, then essentially I've lost some work, or this is performing some work. And the heat contribution would be maybe some heating up of the rope or of the mechanics due to friction. And I always have to invest a little more work to lift it than I will get out from dropping it. This is what the first law of thermodynamics tells us. But of course, what I implicitly assume here is that the entire process is observed all the time. One of the big issues, and this is why I was giving the title of Thermodynamic Limits to Measurements, one of the fundamental problems is that this implicit measurement that I can always assume in classical thermodynamics is no longer true. I mean, it's also not true classically, right? I mean, to really see the weight being lifted, to know how much work I've been doing and to know what the position is and how much work is stored now, I really need to send a photon and reflect the photon upon the weight and then detect the photon with a detector and to know where it is. And classically, this is minuscule compared to the work cost that is stored in the weight. It is minuscule compared to the, like, yes, the photons might also just be absorbed and heat up the weight, but all of this can just be safely neglected. But once I talk about work and heat of a couple of ions in an ion-based quantum computer, about an array of superconducting qubits and so on and so forth, there is a significant cost and a significant back action to measuring. And well, this led, and so long story short, I don't want to go too much into technical details, but this really brought up a debate that still is ongoing, that basically shows, or that asks, well, how can I even define work in the quantum world? So, sorry, my son in the background. Okay, but the bottom line is, I can't just observe a process and without having a significant work cost. And one of the first takeaway messages is that observing does cost you work. I will not be able to build a photon detector without this being plugged into an AC power supply, whatever. I will not be able to measure a quantum system without using a laser or some other system to basically interact with it. And all of these things make the concept of work very tenuous at the quantum scale. And moreover, also the concept of heat, if things are not in equilibrium, you can debate a long time about what heat is. So there is a whole host of literatures. There is what is called this two-point measurement scheme to basically connect classical stochastic thermodynamics with quantum thermodynamics, where you measure a process in the beginning and in the end only, and look at these kind of stochastic probabilities. Like, for instance, you measure in the beginning to see where the quantum weight is down. Then you do something, you measure again in the end when the weight has been pulled up. And then you'll see kind of a stochastic process where there's some probability of the weight being here, some probability of it being here. And then you sum over these probabilities to get an average work. But of course, this neglects all the work cost of observing, and there is a kind of philosophical conundrum. Okay. But moving on to the second law of thermodynamics, I'll just briefly state it in one of the formulations. I mean, there are like Kano's formulation where you say, heat always flows from hot to cold, but that already assumes equilibrium and tensor product structure. Let's start with in a closed in any closed system, the entropy can only increase through its natural dynamics. Now, if we have a closed quantum system, right? So if we have a quantum state rho and it is disconnected from the environment, quantum theory predicts that it will evolve unitarily, right? So the time evolved state, rho of t, will be governed by unitary dynamics, and the unitary is generated by the Hamiltonian of the system. So this will be e to the IHT, if it's a time-independent Hamiltonian, i.e. a closed system that I don't interact with. Now, of course, we also know that a unitary operation does not, in fact, change the entropy. Well, it doesn't even change any of the eigenvalues of that closed system. And yet, we observe closed quantum systems equilibrating. And there's a fundamental mystery to that as to, is there at some level a breakdown of unitarity, or is all the increased entropy kind of a subjective emergent phenomenon that only through very large numbers and impossible complexity turns out to become objective? So what do I mean? So there's kind of two approaches. One of them you might have heard is the Eigenstate formalization hypothesis, which essentially states that yes, even if I have a quantum many-body system, so I imagine, like say I now have many quantum systems and they're interacting with each other, and in a non-trivial way with some interaction Hamiltonian, I have this pair of an interaction, and I have this interaction Hamiltonian has some eigenstate. So let's say I just write a spectral decomposition EI. Well, even if the system, even if I was in a pure state, say in an eigenstate of that Hamiltonian, so even if I was there, or any superposition of eigenstates for that matter, I would not be able to distinguish it from what is called an equilibrium of thermal state that I assign a temperature to. So, which is weird because the equilibrium of thermal state is known to be given as e to the minus beta h over z. Z is the partition function. It's basically just the trace of e to the minus beta h. And now, and beta is just a one parameter family, but it is associated by multiplying with a physical constant, the Boltzmann constant, to a temperature. And now, okay, so how can these two things be the same if they're entirely different states? This is a mixture of eigenstates with Boltzmann probability weights. This is a pure projector on my Hilbert space. In what sense can they even be equivalent? And the eigenstate formalization hypothesis states that all the observables we can conceivably measure, like all the physically reasonable observables, would not allow us to distinguish these two. So in some sense, it's even agnostic as to whether things are truly in equilibrium, or they may just be in a very delicate pure quantum state. We would never be able to tell the difference. So for all practical purposes, thermodynamics makes it a valid and useful description, because essentially the observables I can measure, right, they are usually limited in scope. So for instance, let's say they would be sum over sigma x I inside I, where there's a tensor product presumed. So like I would measure the local spin, the average of the local spins that kind of gives you the magnetization of a many-body system whatsoever. So, and this is what is called a local observable, or maybe there would be two-body correlation functions. And, but like the observables that would be needed for generic interaction Hamiltonian to be distinguishable from equilibrium would usually feature very long-range correlators, things that we don't conceivably have access to in any of the platforms. And that is one part of the answer, this ETH. Another one is dynamical equilibration, where, because you see, if that is the state, then, or if it's in a superposition of eigenstates, and I'm in Hilbert space, these unitaries would basically constantly move it around, right? It's never actually in equilibrium, but if I plot my state space here, the density matrix, if I start here, would actually go around in a big kind of circle in Hilbert space. I mean, at least if it's bounded, I would end up in the same place again, and I would have this kind of circular motion through phase space if I keep evolving unitarily. And the question is, well, why don't I see this evolution? Why does it feel like equilibrated? I mean, okay, I might not be able to tell it from observables, but what happens to the dynamics? And here, the answer from dynamical equilibration is that if I take this, if I take the slightest time average, say between here and here, and basically say I do not have precise enough or infinitely precise clocks, or I don't have supercomputers that compute the dynamics to infinite precision. And as soon as I have some uncertainty in where I am and integrate over a small time interval here, then this integrated state essentially becomes again equal to this kind of Gibbs state. And that is, I think, a very remarkable observation that seems to be true in many systems, but we still don't have a full understanding of how and why things actually equilibrate. And this is very much about the emergence of a classical world out of quantum systems. It's a very basic question. And at the same time, it's also needed to understand the limits of, say, we have a cold atom-based quantum simulator, like for instance at TU Vienna, we're working with, it's like one-dimensional BCs, and we can observe the equilibration of these 5,000 atoms in real time. And even no matter how close the system is. And so, but the question is, how can we avoid equilibration? I mean, old questions from the field would say, make the system integrable, introduce further conserved quantities, but there is essentially, just to advertise, a ton of questions that we don't know. Well, we don't have the answers to. Okay, I think my time is almost up, and I haven't even gotten to the third law. But let me just mention what it is. It can be essentially told as the unattainability principle, and it just tells us that starting in a thermal state, I cannot go to a pure or ground state without spending an infinite amount of resources. So actually cooling a thermal state to the ground state would either take an infinite amount of energy, or if I do it adiabatically, it would cost an infinite amount of time. Then it's the so-called Landau erasure, where it kind of gives me KT log 2. But it basically shows also a profound connection between thermodynamics and information processing, because erasure is one of the basic primitives of any quantum computation. And so this was more of an advertisement, a conceptual overview. And if you're interested, there's a recent paper where we touch upon a lot of these laws, where we basically look at the overlap of Landauer versus Nernst, so like the Landauer cooling cost versus the Nernst unattainability principle, and try along the path of resolving this apparent paradox, which isn't any, to show like what really are the thermodynamic constraints to information processing. And it's just the first step where we look at the asymptotics, and this is kind of a research program that hopefully has many years of fruitful and basic science results that will be relevant for quantum technologies.
Okay. So it's all, yes? Thank you very much, Marcus.
Yes.
Yeah, and thank you for the interesting talk. And now we have time for questions and comments. And just remember, you can write your question either in chat, or you can also raise hand in Zoom. You have such a possibility to just to use raise hand option. So this is yellow hand must appear if somebody know. So, and you're free to ask questions. So, Marcus, I don't see now a question, but I have maybe a question. First question, maybe Alexander Kordyuk has. Okay, Alexander.
Okay, you can continue with your question.
Yeah, okay, thank you. Marcus, I'm just wondering, I know that all activity with, actually I have two questions, yeah? Okay, and what about activity with quantum thermodynamics? I just wanted to better understand what is practical outcome of this activity, because I was hearing that people promise to bring some quantum acous, which may be better than what we have now, or something like this. Could you please comment a little bit about this and how this is related to such basic things that you mentioned?
Yes. So, I mean, of course, first and foremost, like my own interest also lies rather in the basic science principle, like really understanding the emergence of a classical world and the underpinnings of thermodynamics and what it really means for information processing. I mean, I think the first thing I want to say is it's a cautionary tale that if you do thermodynamic things, you shouldn't neglect measurements and information processing, because that is costly. A quantum computer will cost energy, a measurement device will cost energy, and there is no perfect information processing and there is no perfect measurement, as those things are forbidden by thermodynamics. So I think one needs to be cautious when integrating measurements and information processing in any resource theory or whatever of communication or computation, and consider the energy cost. But this is more a foundational thing. On the practical side, really understanding these how thermal states emerge and how they can be manipulated also brings us a bit closer to understanding more direct cooling techniques instead of bulk. Like most cooling techniques are actually quite classical and bulk techniques. And the recent proposal, for instance, I could mention is in the BC, we have recently, so this is like 5,000 atoms trapped in a laser-based potential. By installing a digital micromirror device, we managed to essentially shape the potential arbitrarily. So what we can now do is split the BC into many sub-BCs and let them interact with each other. And by insights from quantum thermodynamics, we now know how to manipulate these microscopic systems to make the BC be its own refrigerator. So instead of basically bulk cooling via classical control, via like Doppler cooling, sideband cooling, evaporation cooling, dilution stages, and so on, we can actually now directly manipulate and control the quantum system. So I think that's one of the main departures. In classical thermodynamics, there is no prospect of ever manipulating the microstate, so they never show up in any of the ideas like of engines and refrigeration, right? Because you can only manipulate bulk degrees of freedom and then hope for the best, like compress a big gas. But you can never like really manipulate the microstate. However, once you're in a quantum computer, there's things like, okay, right now it's not practical, but these ideas of algorithmic quantum cooling, where you basically devise an algorithm that automatically cools a couple of subbits and so on and so forth. And I really do hope that understanding these thermodynamic limitations will become more practically relevant. Although I should say right now, it's only a few isolated examples of relevance and more the promise of understanding.
Okay, thank you very much. So maybe Alexander Kordyuk may ask question.
Okay, I should say that I'm not a theoretician like Andrei, and rather experimentalist. Therefore, my naive understanding of thermodynamic or entropy in quantum system is that real system is never closed, and that usually you have redistribution of due to interaction, redistribution of so wave function, yeah, and due to this entanglement and so on. But I wanted to because from in your language, I didn't understand whether you divided by one system and surrounded, let's say, or and how to trace. Is it really possible to trace in this way, as I understand it, to trace the increase of entropy when you just this interaction of neighboring this it remains of course quantum and no losses, but the number of particles increasing?
Yes. So I mean that is a very good observation. It's actually where this whole field also started a little bit, where you thought, like, say, this is the Hilbert space of your lab and everything that is connected to it, and this is the Hilbert space of your quantum system. Then one of the first results, this is called kind of this typicality approach to equilibration, which is to say that due to the generic entanglement of your system with the environment, you will almost inevitably always have an increase in entropy of the subsystem. And so in some sense, yes, that is one part of it, and that's basically where this idea started. But then the question became a bit more about, like, but what if I like manage to perfectly isolate? Because I really want to isolate my quantum computer as good as I can, but will it nonetheless equilibrate, or will my many-body system equilibrate even if I isolate it to the best degree? And the answer is, or what we see is, yes, it will also equilibrate in a closed fashion, while additionally equilibrating in an outside interaction. There's been this beautiful experiment in Vienna by Jörg Schmidmeier, for instance, where, you know, he prepares a state of 5,000 Rydberg atoms in a BC, in a one-dimensional trap. And so there are some correlation functions you can see. And like, so if equilibrium is here, and this is a function of equilibrium, you see you start out of equilibrium, and we can see the system exponentially decaying to equilibrium when it's closed. And how do we know it's closed? Well, it spends some time in equilibrium, but then there's so-called Poincaré recurrences, and you see the system spontaneously hopping back out of equilibrium after it spent some time there and coming back again and coming back again. And so in some sense, this part of the equilibration, this is really due to the interaction with the outside, yet this internal equilibration is basically how a closed quantum system equilibrates. So there is a lot of nuance, I would say, to that question. And from a foundational point of view, it's very interesting to know, how does it even happen in the first place? I mean, why, like, if we assign the environment like a big wave function psi to environment plus lab, how does this equilibrate? I mean, it's true that if I connect anything in an open quantum system Lindblad approach to like S to an environment, of course it will formalize my system. But how did the environment formalize in the first place?
Okay, so my understanding that the entropy to quantum system can be applied only at local level, just because if on large scale it would be unification with great unification. But I understand this as just loss of information about the system just after measurement. Yeah, after measurement you have some information, and then you start to lose it due to entanglement of this. Okay.
Yes, I mean, I think that's a very coherent view. I would also subscribe to, indeed.
Okay, thank you.
Okay, Marcus, maybe I will use a bit time for my second very short question. Sometimes people who are skeptical with quantum computers saying that the quantum computers of large scales are in principle impossible, because you can, with increasing the number of the size of the system, with the number of degrees of freedom, with the number of qubits, or something like this, yes, a system so there are totally new properties in this, new properties in the system appears. Can quantum thermodynamics say something about this, that we really cannot build very large quantum computers, because for such large scale we don't have a possibility of control, because maybe some very fundamental laws of nature, or this is not the case?
I think it's one very interesting question, but so far we see no evidence for it, neither on the theory side, nor on any experimental effect. So like any decoherence of our quantum computers and large-scale quantum systems is entirely compatible with unitary quantum dynamics. So maybe the takeaway message here so far is rather an optimistic one. So far, neither in measurements nor in many-body dynamics, we see any reason to believe that unitarity breaks down at a larger scale. I mean, it may well do. Of course, we cannot prove perfect unitarity of any even nanoscopic system. However, we also do not need to assume that it does in order to be congruent with the measurements we have. So I would say it's cautiously optimistic on the one hand. On the other hand, it's a cautionary tale in the sense that I need very well engineered quantum systems, because this kind of generic closed quantum system equilibration happens fast if you don't control it well. So you really need to tune the Hamiltonians and the interactions and the timings really well, because once you lose track of it quite fast, your system would be indistinguishable from a thermal state, even if you manage to isolate it from the environment. So maybe that's, on the one hand, it's optimistic. On the other hand, the first takeaway message I would say is, well, perfect isolation is not enough for perfect control. Perfect control is more. It's also about the energy gaps and the precise couplings of the Hamiltonians and the timing of your gates and so on.
Okay, thank you very much for optimism and also for your talk. Thank you very much again. So I think that we can select speakers. I don't know how to do it in Zoom, but we all thank you. Okay, thank you very much. And now we are going to the next talk.